Well, there's a few news articles. This one has got a lot of people very excited. It's been rather known, I think, for quite a while by a lot of us that Tor has limitations, but apparently it's more limited than people had understood. And the argument here, the main limitation that I knew previously was that a large number of nodes are controlled by the US government. And so they have a chance of catching all the packet. The way Tor works is you pass your packets through randomly chosen nodes in a network of donated volunteer nodes. But if one person was to own all the nodes on the path you use, then they could find out what you're doing. And so just like BitTorrent, or just like Bitcoin, the idea is that it should be distributed. So many people contribute. No one person owns a lot of the nodes, but the US government does own a lot of the nodes. And it turns out that you can steer traffic by doing denial of service attacks on the other nodes to get more of the traffic to go through your node. And the other thing, which this guy explained, is he was getting a denial of service attack over Tor. And when he started telling people at the high level, there's only a few companies that really control vast amounts of traffic on the internet. Everybody else buys their service, the tier 1 ISPs. And he was talking to them, and when he started telling them his IP address, they immediately knew which IP address it was. Because if you have a large amount of traffic, then they can see it going through just by seeing a huge amount of traffic. And if you download a large file, then they can just do it by traffic analysis, just by seeing where a lot of bytes are going. So, there's the idea that you're completely hidden yourself behind Tor is not really true. Although I must say, Tor is actually excellent at its real purpose, which is for American spies to send data back home. That's why it was developed by the US military and donated to the world. And they said the point of Tor is all the idiots in the world will start downloading porn and pirate software on it, and that will create a background noise of traffic so that our spies can send data back that will not be detectable in the midst of all that background. So anyway, it's so although a lot of people have too exaggerated an idea of how Tor hides you, and there are various ways to defeat it. Anyway, so Trump has become scarier and scarier, and God only knows what he would do if he gets another term. So this guy, who actually is frequently criticized as not having enough guts to stand up to Trump, the head of the CDC went and testified before Congress, and he said, well, a mask is actually more use than a vaccine. Not only are the vaccines not going to be here for another year, because even if we develop them this year, it'll take another year to manufacture them, but the vaccine is probably only going to be 70% effective, and this mask is like 95% effective. So if you really want to be safe, wear a mask. And we could totally end this thing right now by just making everybody wear masks. That's what other nations have done even without a vaccine. And Trump, of course, hit the roof because for some reason, Trump has decided that we are not going to use masks. And now he's decided to hire a TV celebrity and replace the medical doctors with this guy who says that the way to defeat the virus is to just let it spread and kill people and call that okay. And Trump loves that idea. Although the estimates I heard last night are that it will be 6 million Americans will die. But Trump just pretends that's not true and wants to deliberately spread it and is now issuing guidelines to the states to spread it more. So I'm hiding at home. I don't suppose I'll teach face-to-face for many years because America is the worst nation on earth. We have the worst handling of this crisis and we're getting worse and worse and worse. So if Trump wins another term, we'll have nothing but this raging virus until the end of time. If Biden wins, it'll take him at least a year to undo the damage that Trump has done. So anyway, we should all get used to hiding at home for the foreseeable future, unless you want to get this thing, which I don't recommend, even if you're young and healthy, because it seems to do permanent damage to your heart and permanent damage to your brain. So you really don't want to get it. Yeah, herd mentality. Anyway, but now after he testified and told the truth about it, Trump said, oh no, he was wrong, and called him and got him to totally reverse. And so although he made a careful statement that wasn't completely lies, but I think like everyone else, he's going to have to force Trump to fire him by telling the truth, which is what happened to everybody else that tells the truth about anything important around Trump. And the people that have left said we basically have a inherited dynasty. Anybody that is not part of Trump's family just gets fired, and you're just disposable. And as soon as you're no longer pushing his agenda, you get out. Now, apparently the insect population has gone way down in America. So birds are in fact starving and just dropping dead, large amounts of them, because they can't find anything to eat, which, and the QAnon is growing and growing. QAnon is a Nazi movement based on the Protocols of the Elders of Zion, which was a forged document that came out of Germany almost a century ago, and it was part of the Nazi thing. And the QAnons are essentially Nazi people, and they believe these series of paranoid things, but they're always very closely tied to racism and hatred of Jews. And they believe that you need to like take up arms and kill all the Democrats and kill all the liberals to save the world, and that we're all drinking the blood of infants and killing babies and stuff. And it's getting bigger and bigger. And there are many, many scary things. They're after Scott Wiener because he wanted to do something to reform the laws for pedophilia. And so they say he's a pro-pedophile guy. They exaggerate everything crazily. And there's quite a, yeah, here's more of it. This woman who is now going to be in the GOP Senate, not only is in QAnon, she also is anti-Semitic and believes the earth is flat and that 9/11 was done by somebody other than the obvious people who did it, and so on. And this stuff is going to be mainstream Republicanism as far as we can tell. There are 8 Republicans running for candidate that openly acknowledge this stuff, and more all the time, because now a couple of weeks ago, Trump openly said QAnon is fine. These are great people. They support me. They're patriots. Just like the Nazis who are totally coming out. The American Nazi Party is coming out. And there was a survey. I may not have that one here. Yeah, here's the one. Another fun fact. 2/3 of Americans no longer understand the Holocaust. They don't know that 6 million Jews were covered. And the part that I thought was particularly important is the thing that surprised me. 30% of Americans think that it's okay to be a Nazi. Only 70% of them say they would find it unacceptable in one of their friends to be an American neo-Nazi. And that is what I got out of the last election. I mean, Trump has 30 or 40% of Americans, and obviously they're perfectly happy being neo-Nazis because that's what the Trump regime is. And anyway, it is horrifying and fascinating to watch our society collapse, but we have a chance to save it. And I realized by looking at history, we've had demagogues all through history that have been like Trump. We had McCarthy before him, and we had Mussolini and Hitler, and all the way back to ancient Rome. Democracy is a precious thing and a jewel, but it is unstable. It will self-destruct unless you constantly support it and rebuild it and defend it. It's like balancing a bowling ball on top of a pin. It won't stay there unless you're constantly struggling to hold it up. And so every generation has to struggle and overcome the tendency of democracy to collapse into monarchy, and this is ours. We're going to collapse into a Trump dynasty. Trump has also been again stating that he doesn't really feel like he should pay attention to term limits. And if he gets another term, he should just get another term after that because people have been mean to him. And so, he's making it very clear. Oh, they're also making it very clear that they're going to rig the election. They've done many things. Bill Barr wants to bring sedition charges against the protesters, and a lot of them are now talking about taking out guns and fighting to make sure the election comes out their way. That's the martial law talk, and a lot of this is going on. And this guy here was talking about how he won't be able to buy bullets because everyone's going to get them to hunt down the liberals. The new head of the Health and Human Services, who actually quit. He was taking a leave of absence because he got so crazy, even he couldn't stand himself. But anyway, so let's get down to the official class stuff, which is here. So we're going to do block ciphers today, which are really important. This is really what everything uses all the time is block ciphers. And so it's primarily DES, the old one, and AES, the new one, that we're going to talk about, and the theory of how they work. So let's start with that. And that's here. All right. So we're going to talk about how block ciphers are built and how AES is built. And then, of course, the most important ways it can go wrong. Now, in block ciphers are private key encryption, which is the classical kind of encryption we've been using for thousands of years, where you have a key distribution issue. You have to somehow get a secret key to the other person. But after you've done that, the two of you can exchange data with some degree of security using the same secret key at both ends. And so in the 70s, the United States declared a standard for encryption. And I think before then, people didn't use computers that much, and they didn't really worry about it that much. But they decided then that encryption was an important thing that ordinary businesses and perhaps even ordinary people needed, although they really at that time were only thinking about businesses like banks needing encryption. And they defined the data encryption standard, which and the KGB defined one later. And so that was the standard until 2005. But in 2000, they upgraded it to AES very reluctantly, because the evidence is that the government cannot break into AES, and they totally could break into DES, and they carefully designed it so that they could get in, but they thought nobody else could. But these are block ciphers, and a block cipher, you have an algorithm and a key, and you have a block of text, usually 8 or 16 characters, and you encrypt it and make a block of 16 ciphertext characters, and you decrypt it to get back to the plain text. And all you need is the key to encrypt it and the key to decrypt it. And so the block cipher should create a essentially random output. There should be no patterns visible in the output. It should just be like completely random bytes, and that's the most secure arrangement. If there are any patterns in the output, then you could use those to learn information about the key. So DES uses 64-bit block size, which is 8 bits. 8 characters, and AES uses 128 bits, 8 bytes. And this was designed not because those are mathematically perfect numbers, but because they fit into the registers, because these things were designed to calculate fast. So you could manufacture equipment cheaply that would automatically encrypt stuff and decrypt it to build them into banks and such. And if you have block sizes below 64, then there's a codebook attack we'll talk about. Well, right here it is. If you have, for example, a 32-bit block, then there are only 4 billion possible combinations of 32 bits. So you could just make a table with 4 billion lines that would have every possible output. And so you could just look up the answer, take a block of ciphertext and just find it in the codebook without the key, because you could, that's its biggest rainbow table attack, if you like. That's the codebook attack. So you don't want the block size to get too small. You want the block size to be so big that you can't possibly have enough memory to store that entire table. And 64 bits is probably long enough, but 128 bits is certainly long enough. 2 to the 128 is a monstrous number. You could never possibly have that much memory. So there's 2 ways to make a block cipher: substitution, permutation, and Feistel. And the older system was Feistel, used by DES, and the modern system is substitution-permutation, used by AES. So you have a round, which is some kind of transformation, and then you have a series of rounds. You just do a series of rounds. So you take the plain text and run it through a round, and then you take that and run it through a round, and that and run it through a round. And there's an inverse round function for decryption. That's how they're generally built. So you have round keys. Now you could use the same key for every round, but that would be significantly insecure, as we'll talk about. So what you actually do is you have a way of generating many keys from the original key. So you have a whole series of keys using a key schedule, and then each round uses a different key. If you had the same key in every round, then you would have 3 rounds. Say you have plain text here, you encrypt it once, you get P2 again and again, and then you get the ciphertext. But if you were able to encrypt this with 3 rounds, you get that ciphertext. So this is subject to a sort of meet in the middle attack. You can consider this as 1 step forward or this as 1 step backward, and you'll be able to divide the problem in half. And that's the problem. If you can find plain text blocks that are related, if you can figure out this P2, then you could find a message here and come back. And you know, that's possible. Since there are many identical steps, you can find ways to sort of break it apart and break the steps one by one, and that makes it much more fragile. And we'll talk about the DES, double DES system later, which makes that much more clear. Anyway, all right, and then there's a slide attack and round keys. So this thing here is called, I think, the slide attack. That's the slide attack, where you consider a different case that's related to the previous one because the blocks are interchangeable. So in AES, you have a key schedule created from the key, but it's not random, of course. It has to be predictable. So the attacker can, in principle, compute all the keys from the original key. And so that doesn't mean you can do a slide attack, but it does mean that you can use side channel attacks. If you can measure something like the radio signals emitted by the processor, then you can take the radio created by this round and mathematically relate it to the key. So you can take the radio from each round and get clues about the key, since the key rounds are connected to each other in a predictable way. So that's not a strictly mathematical weakness, but it is a concern. All right, so substitution permutation works by having confusion and diffusion. Now, confusion means that if you change one bit of the key, you change everything. You change half the bits randomly in the output. And diffusion means that if you change one bit of the plain text, you change all the bits randomly in the output. And that's what you want. You want everything to be scrambled so that there's no pattern. And that you can't change one bit of the key and detect that as different than any other change, and you can't change one bit of the plain text and detect that as different than any other change. That's necessary, or there would be a way to use chosen ciphertext attacks and other ones to deduce information about the key. In the Feistel scheme, you encrypt only half of it in each round. You encrypt this round, and then you take that ciphertext and XOR it with the plain text, and that's all that happens here. Then you flip it. So you only encrypt one half each time, but you keep flipping them around, so you have to do more total rounds. But the end result is it can be okay, and that's what DES uses, 16 rounds of Feistel, so that each half does get encrypted 8 times, taking turns. All right, let's take a look at some cahoots about that, which should be here. 4A, all right. This looks like the right class, but it did not open. Ah, there we go. Yes, my Kahoot is loading, all right. This man Spiff is from Calvin and Hobbes, isn't it? I think, yeah. Yeah, well, democracy is pretty terrible, except for all the others. It's the best bad system we know of. It has a defect. It tends to self-destruct, which we're observing. Well, awful lot of people in the room. I think some more might be coming. I'll give it a few more seconds. There's 22 people. So unless 10 of them are asleep already, I would think we'd get a few more. Yeah, all right. All right, looks like 10 is what we're getting. We have Kahoot abstainers. This is like American voter turnout. We only get like half the people voting. Anyway. All right. All right, so what kind of rounds are used in AES? All right, substitution, permutation, that's it. All right, which attack cracks ciphers with small block sizes? You can make a code book with every possible pattern of plain text and the ciphertext that matches it. That's the problem with it. All right. Which one cracks ciphers with fixed round keys? All right, that's the slide attack, since every round is the same. All right, and which type encrypts only half the plain text? All right, that's Feistel. Good. All right, so I've got Daryl. Sounds like a real name. And Juarez, I know who that is. And Democracy, you'll have to tell me who they are if they want their points. Some people don't care. All right. Aha, okay, good. I see your name in there. All right. Oops, I better spell it a little better. There we go. Okay, good. All right, so let's focus on AES, which is, of course, what everybody uses these days. It's the best. There's no reason to use DES except as a mathematical curiosity. DES had a 56-bit key, and you can crack a 56-bit key by brute force. 2 to the 56 is not a large enough number, and you can actually do that many calculations, and you have been able to since the late 90s. So the first step to improve DES was to go to triple DES because there was a bunch of hardware installed and built running DES. And you have to have a transition period when people can continue to use DES for a while they move to triple DES. And triple DES was designed so it was very easy to buy a triple DES device and downgrade it to single DES for a temporary and then upgrade to triple DES later. So, but AES replaced it. Now in AES, it's based on the Rinjail cipher, which I guess is the name of the person that invented it. And we'll see how it goes as we go ahead. And by the way, if you're doing the crypto hack, I did that, you actually build your entire AES implementation over a series of about 10 challenges yourself. And it's really not that hard to do. It's very simple. Every step is a very simple transformation. That's why it's very popular and recommended for everything, because it's very easy and very fast. And the way it works is you make this internal state, which is just 16 groups of 16 bytes. You have 16 bytes in a 4x4 grid. And then you just shuffle these things, just like you might make mashed potatoes. You cube them this way, you cube them that way, you shuffle them this way, you shuffle them that way, just to mix all the patterns out of it. That's all you're doing. So you add a round key, then you substitute bytes, shift the rows, mix the columns, and add the next round key. And you just do that over and over in several rounds. It's just a simple, obvious thing to do. It uses a keys expansion, so every round has a different key. And the adding round key means it depends on the key. Substituting bytes is a nonlinear operation, which prevents it from being mathematically reversed. Shifting rows mixes the columns together so that there isn't a pattern, say, vertically in that column, and the mixed columns is so there isn't a pattern horizontally. So it's pretty simple, and you can do it in Python 3. It's very easy. You just import AES, then you need a key, which has to be 16 bytes, and it could be anything. I use this non-random key, not because that's particularly strong or anything, it's just for demonstration. Then you create a Cipher object based on your key, and you choose the mode, about which we're going to say a lot more later. Now, this uses the unrecommended insecure electronic codebook mode, which is textbook encryption, which is encryption where each block is independently encrypted. So now I put in plain text, and I also make that 16 bytes long. And this is the difference between Python 2 and Python 3. These are not strings. They are byte objects. That's what the B means. They're stored as bytes. So then you just encrypt it, and you can print the ciphertext as hex, and you just have, of course, scrambled random ciphertext. And to decrypt it, you have to make a fresh Cipher object, and then run Cipher decrypt. And then it will turn into your original object, which is the message you sent as a byte string. So if you have the key, you can decrypt it, of course. And if you don't have the key, all you have is this stuff. And there's no easy way to get the key from that. And trying all possible keys would take an unthinkably large number of calculations. So it's really considered very strong and used for everything, everywhere, pretty much these days. So what you can do, if you do the crypto hack projects, you will just have a bunch of Python functions doing every step and learning doing this. And you can do that, but it's slow. Now, what's faster is to have each step stored as an array to just look things up. Each step is simple enough. You can use table-based implementations, but what's really fast is to have them built into the processor, which is the way it's done mostly these days, to make it more secure. So OpenSSL actually uses tables. So each round is just a series of mathematics here, and you see it shifting something over and shifting it this way and mixing different things, just looking up different elements in an array with different patterns. This is each round is for these statements. Let's see, each operation is very simple, shifting things over a few bits, XORing it with something, and so on. Very simple little operations. All right, the problem with this kind of code, where you do it in software, is that it will depend on the key. If the key is simple, then your software will skip steps. So you can measure the timing, and the timing will be different depending on the key. So by measuring the timing carefully, you can gain information about the key. This is the problem with any efficient code. So one solution is to write code that wastes time, so it always takes the same amount of time. It always takes both branches of an if statement, essentially. You can do that, but the better solution, and the one that's almost done everywhere, is to use the hardware. You build the processor with circuits that do the steps of AES, and then it just goes in a certain number of clock cycles. It's always the same amount of time. It's very fast, 10 times faster than doing it in software. And then you just have these assembly language instructions that do a round. So you do an XOR, then you do like the 10 rounds, then you do the last round, which is missing a step. And that's just a fixed series of assembly language instructions that do AES. And you always do that, and it always takes the same amount of time, and it's plenty fast. But of course, it had to be built into your processor, which is why it's real important that we pick a system, perfect it, make it the standard, and stick with it for decades so everybody can do this, design all their hardware and software. And you have to choose a system that's good enough. And it looks like AES really accomplished that. So everyone thinks it's very good. And AES is just the simplest, fastest way to stop every known attack. So they carefully designed it to not have any of the known weaknesses. And so far, it's held up. There are no public attacks against AES that are fast enough to be of any importance. However, there are ways to make mistakes, and one of them is the mode of operation. And these modes of operation were originally defined by the government standards for DES, and they remain the same for AES because this issue remains the same, which is it's a block cipher, so it's really only intended to encrypt one block of data. But what if your data has a different length? Then you have to somehow extend it or break it up into blocks, and that turns out to be fraught with danger. So the simplest thing, of course, would be to just encrypt each block independently. This is electronic codebook. You take a block of plain text, you encrypt it, next block of plain text, you encrypt it, and so on. That would be fine. The only problem is if you have a duplicate block of plain text, you'll get a duplicate block of ciphertext. So that means, for example, here, if I put in dead men tell no and dead men tell no, 16 letters and another 16 letters, and encrypt that, I get 66CC, and down here I just get 66CC2A again, the same input, the same output. So that is a weakness, and it's a pretty serious weakness. And I find a lot of encryption done this way. When I audited the Staples Android app, they stored a local path. They stored a local thing called encrypted key on the phone, which is a bad thing to do anyway, but I wondered what they'd done. And the trick I'd learned from the Web Application Hacker's Handbook is to just make a password with 32 letters, all the same, and then a few other letters at the end to pass their complexity requirement. So this is 16 A's and another 16 A's and then some other stuff. And if you look at the encrypted password, it's base 64 encoded. This is what the Staples actually stores, string name encrypted password, and then it's a blob of base 64. But if you undo the base 64, it's got a block of ciphertext and an identical block of ciphertext. And then the third block is different because those are the extra letters and whatever padding they put in. So this means they are in fact using electronic codebook mode to encrypt the stuff, which is one of the many foolish things about this app. And I found about half the apps I tested did that essentially, this or something similarly stupid. And so if you encrypt an image, you see the patterns. These are gray, 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 blocks of identical gray turn into blocks of some other color. And so obviously this is not good encryption because I haven't really removed all the information in the image. I can still see that it's a penguin. And the idea is I shouldn't see anything. So the general best solution is a cipher block chaining. At least this is the most common solution. Probably counter mode is even better. The lowest counter mode is what's now considered the most secure. But cipher block chaining was a very popular solution here, where you encrypt, you add not only a key, but an initialization vector. And this is not secret. The initialization vector will be stored with the ciphertext and transmitted over an insecure channel. It doesn't have to be secret, but you do need it to do the decryption. Then you XOR the first block with the IV and encrypt that, and then you take the output of that as the IV for the next block. Now, one problem with this is it's going to be slow because you cannot do it in parallel. You can't do block 2 until you've done block 1, and you can't do block 3 until you've done block 2. But it is adding something that's essentially random to each block, so that means you lose all the information. You can't see the penguin anymore. Even though all these blocks are just gray, 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 they turn into random noise all the way across, which is a much better encryption scheme. It doesn't leak patterns out. All right. And so like I say, now if you were to use the same IV every time, then the first block would be in electronic codebook mode. It would always be predictable. So you need to use a different IV for each message. But even if you make that mistake, it only affects the first block, not the later blocks. And so but just anyway, you should have a different IV for each block. The other thing, of course, is electronic codebook could be done in parallel. Is that similar to WEP? Well, it is the same as the WEP IV. Yeah, WEP works. Yeah, WEP was essentially the same thing. However, it made some mistakes. But yeah, it's the same as the WEP IV, I think. Yeah. All right. Anyway, so electronic codebook can be done in parallel. You can have like a 4-core processor, and each core could be encrypting different blocks because each block does the same math. But CBC, cipher block chaining, if you have a 4-core processor, it doesn't do you any good. You only get to use 1 core because you have to do each computation one by one. All right. Now, the other thing, of course, is what if your message is not equal to 16, 32, or 64 bytes? Then, if you try to encrypt something like hello, that's only 5 bytes, this Python library will refuse to do it and say input things must be a multiple of 16 in length. So you have to pad it. Now, almost everybody uses this system, which is a RFC standard, PKCS number 7. And here's how padding works. If you need 1 byte, you use 0, 1. If you need 2 bytes, you use 0, 2. If 3 bytes, you need 0, 3. If you need no bytes, then you add a whole 16 bytes of 1, 0. So you always add padding. And the point of this is it makes it easy to remove the padding once you decrypt it. So you decrypt it, you get all this stuff, then you take the last byte and you remove that many characters. And now you're back to the original message without extra junk added to it. So it has that advantage, but it also means that the last byte of plain text is always chosen from 16, not from 256. And really, yeah. And it also means you can have a padding oracle. Now, this padding oracle is not really a flaw of the mathematics of the encryption. It is a flaw of the implementation. There were systems that made a mistake and gave you an overly informative error message. They would not just say, could not decrypt, something went wrong. They would say, failure in the padding, or failure somewhere else. And that minor change in the error message was enough to destroy the whole thing. So if it tells you the information that the problem was in the padding, and you can detect that, then you can pump out the information about the key. And that's one of the projects you'll go through here. So there are other alternatives to padding, by the way. Here's a cute system called Ciphertext stealing, where you have your message runs out here and you have extra bits. So what you do is you pad it with zeros, but then you take the previous block of ciphertext and you mix it in. So you end up, and then you put this as the output, you swap the last 2 blocks and you mix the last 2 blocks together. So you create padding that is effectively random. And this system is considered quite secure, immune to padding oracle attacks, but it's a little complicated and not too often used. But it is another way to do it so that you don't have anything predictable about this padding. All right. But what's really become the king is counter mode. And this is what's highly recommended these days, in particular Galois counter mode, but this is the simpler counter mode. You have a nonce and you just XOR it with a counter, and then you add one for every block. So each block has this is essentially the IV, and it's predictable IV, but it's not the same in every block. And since you've got confusion and diffusion, so that changing one bit in the IV will change all the bits in the output, randomly half of them, that it's perfectly fine that these are just counting 1, 2, and 3. And now you can parallelize it because all these can be predicted. And not only that, take a look what happens. You feed in the key and the nonce and this counter, and then you just XOR the plaintext with the cipher. So this is in fact a stream cipher in practice. You don't need to pad the message at all. If the message does not fill the block, it doesn't matter because you're just XORing with the bit stream. So this is essentially a simulation of the one-time pad. You've got a system here that takes your key and turns it into an endless stream of bits, and you can use that in a stream of bits to XOR with the message, with the plaintext to make the ciphertext. And decryption is just the same way. So this is cute and considered quite secure, and you can parallelize it. One block does not depend on the previous one, and it doesn't have any padding oracle issue because one block is not calculated from the previous block, and there's no padding. You don't need to pad the message. So it's got a lot of advantages, and that's why I think everyone's pretty much moving to counter mode. All right, so you got these nonces and so on. Use a different nonce for each method, however. If you reuse a nonce, then it breaks like the one-time pad. Because if you use the same nonce again, since the counter is just counting up, you're going to have the same bit stream. And that means those two messages have been encrypted with the same bit stream. And therefore, if you XOR the two ciphertexts, you'll get some plain text. This is a mistake early versions of Microsoft Word made. And a lot of cryptography products have made that mistake. So it's a thing. Here's an example of that. If I encrypt it here and get the ciphertext, if I re-encrypt the ciphertext, I get back to the plaintext because it's just connected by XOR. So if you have to have a different nonce for each one, if you use the same nonce again, you're encrypting with the same bit stream, and that's subject to the same kind of flaws as reusing a one-time pad. All right, but no padding. It's effectively a stream cipher, just a series of random bits. Faster than any other mode. You can parallelize it. You can even calculate it in advance and store it and just have it ready to use because you don't even need to know the plaintext while you're calculating the bit stream. So those are all a lot of handy advantages. Now, the problems, there's two main problems, meet in the middle and the padding oracle. Meet in the middle is a really big category of attacks on cryptography. And so we mentioned before that single des wasn't strong enough, so they moved to triple des. In triple des, you encrypt with the key, and I think decrypt with this, encrypt again with this key and decrypt with that key. There are different versions. You actually use the same, you can use 3 different keys. You could encrypt 3 times, there's various versions, but you do 3 rounds of encryption or decryption. And why don't you use double des? And the answer is, if you did key 1 and key 2, then you would think, if this is 56 bits and this is another 56 bits, that you've got 112 bits of security, and that would be enough. Anything 100 or bigger is effectively unbreakable. But it turns out that is not true at all because of a time-memory trade-off. If all you could do was try combinations of K1 and K2 until you had to try them all, you'd have to try 2 to the 112, and you could never do that. But the point is, you not only got a lot of CPU cycles, you've also got a lot of memory. So what you do is you take your plaintext and take all possible keys, and you store a table of all 2 to the 56 answers here, because that is not an unachievable amount of memory. And then you do the same thing this way. You take the ciphertext and decrypt with all possible keys until you match one of those values. So by using 2 to the 56 cycles twice and 2 to the 56 storage units, you can crack it. So the total amount of difficulty involved is really only 2 to the 57. It is not 2 to the 112. And so this is the fundamental problem, and this happens to a lot of things, and we're going to see this over and over again. If there is some way to break the problem in half, doing the two halves separately lowers the difficulty down to the square root of the number of calculations. So you have to have something that can't be split in half. And triple dash does this. You could pick a spot in the middle, and this would only be 2 to the 56, but the other one would be 2 to the 112. And there's no way to split, again, because you don't know either end of this one. So that's why you can use triple dash, but you only have 112 bits of security from triple dash. You don't have 112 plus 56, which is what you might think. All right. And then there's the padding oracle, which is very nice. And so in the padding oracle, you do cipher block chaining. This is the one where every block of data is encrypted, and that turns into the IV for the next. So here's the encryption. You feed in an initialization vector, you XOR it with the plain text and encrypt, and you use that as the IV to XOR it with the next plain text and encrypt, and on you go. Now suppose I have a message that's only 47 bytes long. Then I'll have a padding byte here. All right. Now consider decryption. This is how decryption works. You feed in the initialization vector and the ciphertext. You decrypt the ciphertext, and then you XOR the IV with this output to get the plain text. The next time, you take this ciphertext and XOR it here, and that ciphertext and XOR it here. Now remember, the attacker typically has access to the ciphertext, but they don't know the key. So the attacker knows this ciphertext, and it's related to the plaintext by just an XOR. So suppose that the padding byte is right here. Now, what I do is I change one byte in the second block. If I do that in the ciphertext, when it decrypts, that's going to diffuse and mess up all the blocks here. So I'm going to garble this message entirely. But that doesn't affect the next block. The next block takes the ciphertext and XOR it here. So if I change this byte, I only change that byte of the plaintext. So now I have lowered the complexity from a 128-bit key down to an 8-bit key. I'm able to manipulate this byte by changing just one byte up here, and there's only 256 possible values. That's decreased the complexity greatly. So what you do is I try all 256 possible values here. One of them is going to be the original ciphertext, which I know, by the way, and that'll of course be valid. And the other one will be when that equals 0, 1. That will be interpreted as valid padding. So the padding error message that tells me if the padding is correct enables me to deduce this number. And I can gradually go back byte by byte, and I can deduce this number, and then I can forge any message I want. I can make these 16 bytes decrypt to be any message I want. So I've not got the original plaintext. What I've gained is the ability to forge a message which will decrypt and create certain readable messages at the other end. And that I shouldn't be able to do. So that's the game. You continue byte by byte until you learn this entire orange thing, which you don't know the key, but you do know this value, and you can use that to forge any message you want here, as long as you're willing to accept totally garbling up part of it there. And in practice, for a lot of computer systems, that is enough to gain control of the system, because they have you encrypt something, and when you're able to encrypt something that decrypts correctly at the other end, they take that as authentication, proving you're the administrator, and then they use that message, and it contains commands, so I'm able to add commands and create messages which are interpreted as authentication and action items at the other end. So that's the padding oracle attack, and it's very easy to do with Python, and you'll be doing it in the projects. So I'm trying to get this thing to go to like cahoots. There they are for B. All right. All right, that might be all we're going to get. I'll give it a few more seconds. All right. Aha, okay, good. Wait a few more and see if anyone else is coming. All right. All right. What system exposed AES to timing attacks? Okay, the tables take a different amount of time to look up different elements, apparently. All right. What system is vulnerable to padding Oracle? Cipher block chaining, because it relies on this strange thing where the output of one block affects the next block. So you can reverse that and use it to manipulate a block. All right, which one requires special processor instructions? Okay, that's native instructions. And like I say, that's why you really need to have a standard and you really need to stick with it so people can build hardware and keep using it for a while. All right. What system leaves the penguin visible? The famous attack. That's the electronic codebook. Reveals large-scale patterns in the input data. All right, and which one converts AES into a stream cipher? All right, that's counter mode. All right, so let's see. We've got 43, you'll have to tell me who they are if they want their points. And democracy, I know who that is. Okay. And Juarez, I know who that is. All right, good. So, all right, I think I'm just going to point you to some projects. I don't really think it's worth demonstrating them particularly, but the ones particularly related to here is where you do that one with the penguin, which is very simple. You download this image, and then you run your Python 3. And of course, that image turns out not to be an integral multiple of 16 bytes. So if you try to encrypt it just the way it is, it'll tell you you can't do that. It has to be aligned to a block boundary. And the other thing, of course, is if you were actually to encrypt the entire file, it would no longer be a readable image file at all. So what you do is you take that image and you just throw away, you remove the last 2 bytes and you skip the first 64 bytes. So you're going to encrypt everything in the middle. And keeping the first 64 bytes unencrypted means it'll still be a readable image. And the last 2 bytes being unencrypted technically means some portion of it is not completely encrypted, but it's good enough for our purposes. And now you can encrypt the trimmed part out of the middle and then rebuild it, the first 64 bytes, then the encrypted stuff, then the last 2 bytes, and save that as a file. And when you open it, you'll see what we said there before. You see a blurry penguin because this is electronic codebook mode. And if you do it with cipher block chaining mode, where you add an IV here, then of course you get the goodies here. So that's a nice thing to go through, and at the heart of AES. Now, here I got a question here. Can I elaborate on a slide attack on block ciphers with identical key? Well, yeah, I don't think I can express it formulaically. The best thing I've got there, yeah, I was a little vague on it. The one I really understand is this one, which I think is a special case of it. If you have this triple dash, then you know you can do one step and enumerate all of these, and you can do these two and enumerate all there, so you get to lower it by one step. But yeah, I was a little hand wavy on that. You're quite correct. This one here, where you have multiple rounds, yeah, this one. No, not that one. Oh, that's actually a special case. The one where you don't have round keys. This one. I don't really understand the fundamental principles of this one. But if you can solve, that's all. If you solve one round where this turns into that, then you've also got a solution here, but I'm not entirely sure why that is so helpful. The only case where it's obvious is when you have just two total rounds, and then you've got the meet in the middle attack. So I don't think I can add much more to that one. All right. But the other thing I wanted to show you, now of course there's the cipher block chaining attack, which is down here, excuse me, padding oracle attack, where you just go through it here. And so what you do, this one has a high value extra credit thing, which you can do. And I've only had a few students every semester ever do this. So first you go through it here. You have 3 blocks of text. So you have 47 bytes. And this one you change. And now you can just do it in Python. So you encrypt this stuff, and then you change that byte there, byte number 31. And you go through a loop in that byte, and you find out which ones are accepted. So here's what happens. If you change that one byte, all these bytes change in the ciphertext, and this one byte of the next block. So this one does collateral damage here, and it does controlled alterations here. And so you can now try all possible values of that. And when you do, you will find that you get a padding error almost all the time. And so here, if you just try 5 values for it, you get a padding error every time. But if you loop through all 256 values, you will eventually find that some of them don't give you the padding error. There are 2 values that don't. One is the original unchanged value, and the other one is the one that creates a final byte of 1. So now you know what value to put here to create a 1 there. So if you XOR those 2 numbers together, you've deduced that orange value. And you can now go do it block by block, and you can deduce all these orange values, so you can forge a message that ends in up to 16 letters of your choice. So that's the game here. And you can go through the exact challenge here, where you have step by step and the commands to do it. And now you can create something that will encode with a win in it. So the original plain text was a loser, but you've added a winner, a word win to it. And then there is a challenge, which is here for 50 points. There's a board, and you can put your name on the board, but you're going to have to, without the key, deduce a ciphertext that adds your name to the board. So what you have to do is have best if you make a short version of your name, because it's a lot of work to do every byte, and then you put a colon. And what it's going to do is, if it passes the test and it's valid ciphertext, it'll look for a colon and take the part after the colon and put it on the winner's page. So you'll see only a few people. I did a bunch of examples, and then this person, DY, did it. Nobody else has done it this year. I clear this board now and then. So that's worth a lot of points if you do it. Anyway, I just wanted to mention a couple other projects, because I've been doing some exciting stuff. Crypto Hack is fantastic. I highly recommend checking that out. but I got into homomorphic encryption. Homomorphic encryption is almost science fiction, but I managed to get 2 versions of it working, so I added them to the class. Homomorphic encryption is how you make, suppose I have a medical database like Kaiser. Kaiser, if I'm a member of Kaiser, I can log into my Kaiser account and then get information about my Kaiser medical treatments and stuff. So that means somewhere on a server, Kaiser has everybody's medical treatments in a big database in something like SQL Server, and it's all unencrypted. So when I log in, I send my data up there with encryption, HTTPS encryption, and I send them my data, and they then pick off my data and send it back to me. So that's fine as far as I'm concerned. But it means if somebody was able to infect Kaiser's server with malware and steal the contents of RAM, they would get all the database. And that's what happens with ransomware attacks and other attacks. People steal the whole database, then you have a data breach, then you have to pay a ransom, then you have to send out letters and apologize and everything. It's no good. And Target found out that if you put credit card numbers in RAM, they can get stolen from RAM. That's what happened to them. They were not storing them on the disk unencrypted, but they were in RAM unencrypted. So the homomorphic encryption is where you can never decrypt the data at all. You leave the data encrypted in storage and encrypted in use. You give it a query, say, I want my medical data. It encrypts the query. It then runs an encrypted query operation on an encrypted database, picking out only the data for me, and it only decrypts that and sends it back to me. The rest of the data is never decrypted at all. This is a brand new kind of encryption. It was invented in 2009. And as you can imagine, it is very complicated and very slow. So this is the Microsoft implementation of it called SEAL. So if you get a Windows machine and you put on Visual Studio, you can implement this thing called SEAL, and you can see it do a very simple activity towards the end where you make your own project and it uses the SEAL library. And then you can build these examples, and these examples have extensive comments and demonstrations so you can see it do a few simple things. Yes, the Kaiser data has to come back to you. Well, of course, it will be transmitted in transit with HTTPS, but ultimately it has to be decrypted so I can see it. So the point is, it's not to protect me on my machine anymore in the current system, it's to protect the server. So if they infected my machine, they could steal my data. That's a good question. I think it would be decrypted on the server and sent back to me. So that if they were able to store all the RAM from the server, they would get my data at that one time, but they would never have access to the whole database. That's the idea. That's my understanding of it. Anyway, so here you've got these lengthy comments in the code that explain what's going on and these demonstration projects. So you can play a few of them and get some idea how this works. This is the first version of homomorphic encryption, which is kind of insane and self-destructive. It uses lattice encryption and learning with errors, which is also important because this is the prime candidate for post-quantum encryption, encryption that cannot be reversed even with a quantum computer, but it actually destroys the data when you use it. It adds errors to the data and cleans them off. And so the more computations you do, the more noise appears in the data until it becomes useless. So that is kind of crazy. And there are more advanced modes available that prevent that. And then I went to IBM Z, which was the IBM conference where they talked about doing this stuff on mainframes. And IBM is real proud of their product, and they have something called the IBM Encryption Toolkit, Homomorphic Encryption Toolkit, which I got, and I put it here. You have to run it on a Mac, and it runs in Xcode. Just like the other one, you have to run on a PC in Visual Basic. But this one is amazingly easy. Once you get this thing on your machine, you then run these things. And this one here is a search just to find the capital of a nation. And they have about 30 nations. And that is the query it does, but it's all done with homomorphic encryption. And it is so slow that it took 5 minutes to do a search through 30 options on my machine. So they said the original versions of homomorphic encryption were 1,000 times slower than unencrypted stuff. And they said this one had now been improved up to 50 times their mainframe version, but obviously this one is apparently the old one that's 1,000 times slower, because that is horrible. And there's another one here where you do a privacy preserving search. And that's here, credit card fraud demo. They have this credit card system, and you're trying to do a query, and it does it like 21 times, and you see how often it works. It sometimes is correct and it sometimes is wrong, because to make it faster, they increase the error rate so high that sometimes it fails. So anyway, those, you can see how they work. At least you can get a couple versions of this insanity running. If you're interested, of course, none of that is remotely practical now. And considering how slow it is, it may never be practical, but there is a commercial product called Inveil that's advertising all over the place, selling homomorphic encryption, saying, we have closed the final gap in security. You can now keep your data encrypted even when it's in use, which sounds pretty good, but I must say, I don't think it's remotely practical until they make it faster. Even 50 times performance penalty is asking for an awful lot. But Kaiser, Kaiser would transmit the data back to you, of course, with HTTPS, I would assume. Anyway, so those are there if you're interested, and there's quantum computing. These are all very science fiction-y things that are of no immediate value. Things like RSA and AES, you really want to learn and use right now. But those are for people who are sort of interested in looking in the future. Anyway, I think I'll stop this recording, and I'll stick around to answer questions.